Hi everyone. So this is the fourth video for algorithms analysis, and in this video I'm going to do an example of how to analyze a recursive function. Okay, so I'm not going to go over how to do recursion. This is really just how do you analyze something that is recursive. Okay, now first of all, the process of analyzing something that is recursive is not actually different from analyzing something that is not recursive. The algorithm actually is exactly the same, but the way that we do it is exactly the same. It just happens that the code that we're analyzing looks different. And so we just have to be kind of careful about how we do it, but we're still following the same 5 steps. Now, if you don't know what those are, you should watch video 3, which actually does an example of what the 5 steps are and goes into that in a little bit more details. So I'm just going to follow exactly the same steps as I did in video 3 for a iterative function, and I'm going to apply the same steps to doing a recursive analysis because it's actually exactly the same steps. There's just a little bit more math at the end to sort of get to work. Okay, so let's begin. So so I'm going to be analyzing this factorial function. You're all probably very familiar with this function. You probably have written it. How do we analyze this? Okay, so first of all, just like in the third video, I should say, we start by declaring our variables. What is our data size? Start with what is our n, okay? So let's begin with this. Let n represent, now what exactly in this code is the data size? What determines how many things, how many operations I will do? Well, perhaps it's not obvious, but there's only actually one argument here. It's number. And number is the thing that we check to get out of our recursion. So really it's number. Okay, now that's not always going to be the case. Sometimes it would be, like there are situations where you're checking something, but that something is not like for counting, and you would have to think about things a little bit differently. But in this case, our n is represented by number. Okay, number represents, or n is the value we're passing into the function. That determines how many operations this thing will do. So let n represent the number passed to the function. Let's start with that. Okay, that's our data size. So n is whatever value number is. Okay, let t at n represent the number of operators done by the factorial function when given n as the argument. So whatever you pass in, this function says that's how many operators it will do. Okay, so whatever value you give to factorial, that's how many operations it would do. Now, when you're doing a recursive analysis, you really need to know what this means, because this actually comes into play when you're doing the analysis, when you're doing your count. So make sure that you are clear about this. T at n is the number of operations it will do when given n as the argument. The thing, if you pass in n, T at n tells you how many operations this function will do. Okay? Now, this is really, really important. So that's step 1, establishing my variables and functions. Now we're on to step 2, which is counting operations. So we're just going to do it just like we did for the linear search example in video 3. We're just going to count operations. Don't make up code that isn't there. Just read what is there. So in line 8, I have one operator, right? And I do this operator no matter what number is. So no matter what number is, this operator is done exactly one time. RC equals 1 happens once. Doesn't matter what number is. So we count it as 1. Next, we have this. If number is greater than 1. So no matter what the value of number is, that greater than operator happens one time. It's not 10 times, it's one time, right? So we count it as 1. So this is not anything different. So just because this function is recursive doesn't mean we do anything differently. We're going to do exactly what we did before. Okay? Next one. Now this one is this one's a little bit harder. I'm going to skip it and I'm going to go to the very last line. Oops, I have a semicolon here. Sorry, that's my bad. No semicolons in Python. So this should have a 1 because no matter what we do, at the end, I have a return statement that happens one time. Okay, so those three are 1. Now, this line number 10 is the one that's going to give me the most trouble because it has more operators on it and it has the recursive call. So how many operations is here? Now, let's start by just looking at symbols, operators. What are my operators? So I have an equal sign, a multiplication sign, and a minus sign. So I have 3 operators that are just symbols, okay? So I'm going to start by saying, well, I see 3 operators, so I'm going to count 3 first, okay? Now, you go, well, but what about the recursive call? Well, yeah, we're going to count that too. So other than those 3 operators, I'm also going to make a function that is a recursive call to this function, right? So how many operators will that function cost? So remember in video 3, I said that we counted len and range as 1 because they were constant runtime, so we just count it as 1. But you actually have to figure out how many operators this function call is going to cost. And this function call is not constant, so we can't use 1 for the function call. So how many operations will this do? Well, the answer is I don't know. I don't actually know this, and it depends on the analysis. So what you have to be careful of is not to say something like n, because you don't know what the runtime of this function is. Okay. You also can't use like even n minus 1, again, because you don't know how many operations it will do. But what we do know is we're making a function call. And what we're passing in is whatever number was minus 1. That's what we're giving this function, correct? And if we do that, take a look at this definition. T at n represents the number of operators done by the factorial function if we give it n as the argument. So if I want to know how many operators a factorial function call is going to cost me, I can actually express it in terms of t. This will be t at n minus 1. The reason for that is because when I'm going to make this a little bit wider here. The reason I do this, the t at n minus 1 here, is because I'm making a function call. I'm calling the function. The function is going to cost me something. I don't know what the cost is, but I do know that this function t at n is supposed to tell me what the cost is, right? So I'm going to use it. This function tells me how much it will cost given whatever argument I pass in. So since right here I'm passing in n, this is passing in n minus 1. Now, if this was passing in a different thing, like n divided by 2, for example, well, then this would be t at n divided by 2 instead. So it depends on what you're calling this with that determines what's inside here, okay? So this is our operator count, okay? So this is step 2. We're done with step 2. Okay, it's a little bit weird because we have something here like this, but how we fix that is in step 3 and 4, not this next step. So step 2 is done. Now for step 3, what we're going to do is we're going to state t at n. Now again, we're not going to do anything different from the previous, the one in our 3rd video. We're going to do exactly the same thing. We're just going to take everything and we're going to add it all up. So 1 plus 3 plus t at n plus minus 1 plus 1 more. So this is doing exactly what we had done in the previous video. We're just taking each of the comments and we're putting a plus sign between them, adding it up. And now we're going to solve this equation, or we're going to simplify this equation. So if I simplify this, what I'm going to end up with is t at n minus 1 plus 6. Okay? And that is that. That is that. That is how we get there. Now, this, unfortunately, doesn't have a dominating term because we haven't gotten rid of this t yet. So this t at n minus 1, if it's here, we can't actually figure out what the big O is. We have to actually solve this recurrence relationship before we can actually establish what the big O of this function is. So we have to do some more simplification. Okay. Now, how do we solve this? Well, let's start from the other direction. Okay. So what if I were to give you, what if I pass in a value that hits a base case? So for example, what if I gave you the number 1? What would happen if I passed 1 in as the argument? If I took 1, passed it in as the argument, this statement would be false, right? So here, I'm going to take this code. This is for n greater than 1. This is the operator count. But for n equals to 1, the operator count is actually different. If n was equal to 1, okay, oops, if n was equal to 1, then the operator count is going to do the following. We're still going to hit this first line, so we still count it. We're going to hit the second line because we have to do the check. But we're not actually going to be doing this recursive call because if n is equal to 1, the if statement is completely false. And since it's false, we're going to skip past the thing inside the if and go straight to the return. And so for n is equal to 1, I'm going to put this here. For n is equal to 1, t at n is actually only equal to 3. So t at n is equal to 3 if n is equal to 1. So t at 1, and by the way, you shouldn't use n here. You really should use 1. So t at 1 is actually 3. Okay? Now, this comes into play when we try to put this together. So t at n in general is equal to t at n minus 6, t at n minus 1, sorry, plus 6 for all n greater than 1. T at 1 is equal to 3. Okay? Now, we're going to use this idea for t at 1 to sort of put together this is how we get to the final result. So let's think about what the statement says. We're going to start with this expression right here. Now, this is t at n. What is t at n minus 1 going to be? Because I want to know this. Well, t at n minus 1 just means we pass one value smaller than n, right? So if I think about what would happen if I made the function call originally using n minus 1 here, then this would be n minus 1 minus 1, right? So this would be n minus 2. So in other words, t at n minus 1 is actually the number of operators it would take to call with n minus 2 plus 6, because there's 6 operators in that one function call, plus the function call to t at n minus 2. Now, having said this, what is t at n minus 2 then? Well, t at n minus 2, that's just t at n minus 3 plus 6. And t at n minus 3, well, that is just t at n minus 4 plus 6 also, and so on and so on. Now, at some point, if we, like this is going down by 1 every time, right? So n minus 1, n minus 2, n minus 3. Eventually, we're going to get to t at 2. What is t at 2? T at 2 is really just t at 1 plus 6, right? But here's the thing. We actually know what t1 is. T at 1 is 3, correct? So what we can say is that t at 2 is actually equal to 3 plus 6. Okay, because we know what t at 1 is. So at this point, we actually have a number. Okay, now I don't actually put these numbers together at this point because it doesn't help. Okay, so don't turn this into 9 at this point. So how does all of this help? Well, we can do substitutions. So what that means is that if we started off at t at n, well, this is t at n minus 1 plus 6, right? But that is this expression here. So I'm going to exchange this. I'm going to take this statement and I'm going to just replace it with t at n minus 2 plus 6. But what is t at n minus 2? Well, that is this expression right here, right? So t at n minus 2 is just this thing. So I'm going to take this and I'm going to replace this expression with t at n minus 3 plus 6. And what's t at n minus 3? Well, that's just t at n minus 4 plus 6. So I'm going to take this and replace it with this, right? And dot, 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 dot. eventually, I'm going to be replacing it with whatever T2 is, right? I'm going to get to T2, and it will be T2, T at 2, plus a whole bunch of 6's. And that means that this is going to end up being 3 plus, but T at 2 is this. So this is going to end up being 3 plus a whole bunch of 6's. Okay? Now, the only question that we have left to answer is how many 6's, right? So how many 6's are in this expression? Well, let's see. And here's a way to sort of figure out how many 6's there are. When it was T at 2, how many 6's are in this expression? There's 1, right? What would T at 3 have been? Well, T at 3 would have been equal to T at 2 plus 6, right? And T at 2 was equal to this, so we can replace here. Now, that means that T at 3 is 3 plus 2 6's. Do you see the pattern? When this was 2, there was 1 6. When this was 3, there were 2 6's. So if you see the pattern, then you can apply it, right? So what would T at 4 be then? T at 4 is going to be 3 plus, it's going to be T at 3 plus 6, right? So how many 6's are here? Well, we do the substitution back in, right? Take this, substitute the expression, and we get that. So if at T at 4, there are 3 6's. So what's the pattern? Well, it means that for T at n, there are a total right here. There is a total of n minus 1 6's. Okay, so we have n minus 1 6's added together. Okay, now what is another way of taking n minus 1 of the same number and adding it together? What is repeated addition? Well, repeated addition, taking the same number, adding it over and over and over again, that's just multiplication. So this is actually equal to 6 multiplied by n minus 1, because we're taking n minus 1 6's and adding them together. That's just multiplication. So we do that. And now this is much easier to simplify. This is 3 plus 6n minus 6, which is equal to 6n minus 3. And that is the equation that represents the number of operations done by the factorial function. Now, with a caveat, for all n greater than 1, okay? So it's not for every single n. So you should add that little caveat in. But what we have is we have an equation. And once we have this, the last step of stating the big O is just the same. You're going to start by, you're just simply going to say that T at n is, therefore, T at n is big O of, and, well, find the dominating term, 6n, drop the constant on it. What we have is n. So there we go. There's the analysis of the factorial function. Okay? So, well, that's it for this video. Thanks, everyone.